Okay, good. So now we welcome Alexandre Pannier, who will speak about large and moderate deviations for stochastic Volterra systems.
Okay, thank you for the introduction, and thank you. I'd like to thank the organizers for inviting me to speak today. So this is joint work with my advisor, Antoine Jacquier, and as you just stated, my title is Large and Moderate Deviations for Stochastic Volterra Systems. So I'm afraid there won't be any numerical analysis in this talk. So naturally, I'll start by introducing what stochastic Volterra equations are and why we're interested in them. Then we'll talk about large deviations theory. That will lead us to our main results, and finally we'll come back to the initial motivation of our study. So we call stochastic Volterra equations the following equation here. It pretty much looks like a classical E2SDE, except that we've added this kernel K that can be taken singular. What I mean by that is that as S tends to T, K of Ts blows up to plus infinity. So this is a much richer thing than just E2SDEs. So the motivation, our motivation at least, to study such equations comes from mathematical finance, and in particular, it's a conducive framework for Ralph volatility models, which became very popular lately. And the additional challenges compared to an E2SDE that those equations pose are that usually the solution to such an equation is non-Markovian and is not a semi-martingale. So this introduces significant loss of analytical and numerical tractability. So for instance, you don't have access to any ETOS calculus or any type of Feynman-Katz PDE or things like that. So one needs new tools to be able to study those equations, and we decide to rely on asymptotic methods. And in particular, we want to look at large deviations. So the actual definition of a large deviations principle is written in the middle, but I think if you're not already familiar with it, it's maybe more intuitive to think of it as in the following heuristic at the top of the slide. So if you think of a sequence of random variable x epsilon that converges in probability to a deterministic limit x naught, then the LDP for x epsilon will characterize on an exponential scale the rate of the convergence of x epsilon towards x naught. So you can think of it as this equation, and it characterizes this rate of convergence through the so-called rate function I, which is written in red here. We'll see later on what I looks like and how it arises, but for now, let's just stick with this. And the other thing in the title is moderate deviations, or moderate deviations principle will be called an MDP. So it's tightly connected to an LDP because we say that x epsilon satisfies an MDP if eta epsilon satisfies an LDP, where eta epsilon is just a centered and rescaled x epsilon. Note that the root epsilon times h of epsilon goes to 0, which means that this may blow up. Now, what's interesting with the MDP is that depending on your choice of h epsilon, it bridges the gap between the large deviations regime, where beta is equal to 1/2, and the central limit theorem regime, where beta is equal to 0. So if large deviations look at quite rare events, then moderate deviation look at less rare events, and the central limit theorem would look at the not rare events, in a sense. And again, we'll see later examples of LDP and MDP and how they're different. So we're interested in particular in pathwise large deviations, which means that we want to look at the law of the whole path of x epsilon and not just the marginals of x epsilon. The two most important results in pathwise large deviations, the classical results, are due to Schilder, who studied the rescaled Brownian motion, and Freidin and Wenzel, who studied the solution to the rescaled SDE. I said it has to be rescaled because remember, we want the limits to be deterministic. So you want that in the limit, the noise vanishes. I won't go into the details of how they were proved or what it means, but I think it's important to notice that the rate function that I wrote as IW and IX both have the same form. They both features this red function, which is sometimes called an energy function, and where V can be thought of as a control that controls the equation that phi has to satisfy, where phi is the argument. So heuristically, one can think of the rate function as a distance between phi, the argument, and x naught, the limit of x epsilon, which is measured by this energy function. Right. So a little bit of literature now. So Freilin and Wenzel, whose result I just presented, used an approach that has now become standard, which is called the Freilin-Wenzel approach. And it goes like this: you start from a known LDP, and you use a series of approximation to transfer the known LDP from one process to another until you reach the desired process that you want an LDP for. So this is proved efficient. In particular, I'm going to cite two results that comes from graph volatility, because that's where stochastic Volterra equations has been studied the most. So it's been used to prove pathwise large deviations for Rath-Bergomi model and the Rath-Steinstein model. But the impediments of this approach are at least threefold. First of all, as I just presented, like what the approach looks like, you can't have a universal proof, universal type of proof that would give you an LDP for a large class of results. So you need a series of approximation has to be tailored for each model that you want to study. So you need a new proof for every model. And the second thing, which is related to this, is that every time you make an approximation, your rate function becomes more complex. So you might end up at the end with quite intricate rate function. And finally, this approach is apparently not suitable for moderate deviations at all. So if one wants to do moderate deviations, then we have to rely on something else. And what we choose to use is the so-called weak convergence approach, which has been proved to be efficient for stochastic Volterra equations in the past, both for LDP and MDP, even though under quite restrictive assumptions. But we'll show that not only is it suitable for both large and moderate deviations, but it can be used to prove those for a general class of equation that we'll take the form at the bottom of the slide, where this weird theta epsilon has to go to 0 such that the limit is deterministic. And moreover, we'll show that we can relax quite a lot the assumptions to include non-Lipschitz coefficients and singular kernels at the same time. But before going to our remaining results, I'll start by introducing what the weak convergence approach looks like. So it relies crucially on the fact that the Laplace principle, which is written at the top here, is equivalent to the large deviations principle. In both cases, the rate function I of x in red plays the same role, but in the Laplace principle, the left-hand side is with an expectation instead of a probability. So if you want proving a Laplace principle, you only deal with linear analysis, and in particular weak convergence, whereas in large deviations principle, you have to deal with the probability, so that may lead to some nonlinear analysis. And so what Dupuy and Ellis presented in their book of 97 is how to use this weak convergence approach efficiently, how to prove a Laplace principle efficiently. And the method relies on the so-called representation formula. And here I present the one that was proved by Buet and Dupuy in the 98 for the Brownian motion. That's maybe the most technical bits, but if you look at it, essentially, on the left-hand side of the variational representation, you recover something similar to the left-hand side of the Laplace principle. And on the right-hand side of the representation formula, you already recover this red bit, this energy function, which we know has to appear at some points into the rate function. So we already have something quite similar, which is promising, right? Now, what's interesting with this formula is that in the proof, one can recover all the main ingredients, the usual ingredients that one would use to prove an LDP, and in particular, the Gersanov theorem, which means that we're going to use different probability measures. And as a matter of fact, the expectation of this energy function here is exactly equal to the relative entropy between the measure under which W is a Brownian motion and the measure under which the shifted W, so W plus the integral of VSDS, is a Brownian motion. That comes directly from the relative entropy, which can also be thought of as a sort of distance between two measures. And on the other hand, we have this functional of a shifted Brownian motion, which will become very important, and you'll see again how it arises, and that is the starting point of why we have controls in our rate function. Okay, so just keep in mind the energy function and the shifted Brownian motion that we have here. And now I'll show you the structure, the usual structure of a proof of an LDP in the weak convergence approach. So that will highlight the main steps that one has to make and the main assumptions that one has to make, and those that we can relax and those that we can't. The first assumptions we cannot relax. The first assumption is crucial. One needs to have strong existence and uniqueness for this equation, which is the model that we consider. The reason is that we want to be able to write x epsilon as a functional of the Brownian motion. Now that we have this, we can use the variational representation, which means that we end up with a functional of a shifted Brownian motion, where the shift is written in red, and we can identify this functional of shifted Brownian motion with the solution to a controlled equation, which is written here, where the additional red term is controlled by V. And that's really, I think, the important bit. So the first two steps we cannot really play with. But the third one is where the convergence, and hence the name of the approach, takes place. Now we have to make the right assumptions such that x epsilon V converge to some limit xv, and be able to identify xv as the limit of some equation, which is not surprisingly written like this. And this Volterra equation also is controlled by V. This is the step that you can play with. And the last step is to use the uniqueness of this limit equation to be able to write down the rate function, where again the energy function appears in red, and phi has to satisfy this equation. Now, what we did is that we played a little bit with the fourth step as well. We relaxed the assumption of the uniqueness of the limiting equation in a way that is a bit abstract, so I won't go into the details of that. I'll show in the end one example of an equation that does not have uniqueness but still fits into our framework, and for which we can recover LDP and MDP. Okay, so now goes the two main results that we have. The first one is the LDP. So as I mentioned, the first assumption, pathways uniqueness, is non-negotiable. The second one is on the regularity assumptions on the kernels. So it includes all the main kernels that one can find in literature, including the singular ones, and it's essential to prove the weak convergence of x epsilon V. The third assumption is some assumptions on, of course, the coefficients, which we wanted to relax as well, because we have in mind some applications to rough volatility where linear growth may not stand all the time. And we wanted to be able to allow for some exponential growth under certain conditions, of course. But again, we'll see an example in the applications of how this can be applied. And finally, as I said in the previous slides, the limit equation may not be unique, but I won't go into the details of how we relax that assumption. So all in all, under those set of assumptions, which are quite wide, we prove pathwise large deviations for the family x epsilon with the rate function I that we saw in the previous slides. And the other result that we have is for the MDP. The structure of the proof of the MDP is very similar to the one with the LDP, except that one has to deal with a different kind of process. One has to deal with eta epsilon, so the rescaled x epsilon instead of just x epsilon. So the proof of the weak convergence is different, but the structure is similar. The assumptions are similar as well, but what's important to notice is that the limiting equation, which appears at the bottom in the rate function, is quite different. There are two things I think that are important to notice. The first one is that the gradient of B appears which means we have to assume that B is at least C1, and in fact, globally Lipschitz is continuous. And the other thing is that the equation is actually linear in psi. So we don't need to assume any uniqueness because it's almost for free. And since it's linear, it will also lead to better understanding and a more tractable rate function in the end, because we only have to deal with, well, a linear Volterra equation. So that's it for our two main results. And now we'll see how quickly how one can apply those to graph volatility models, and in general, what kind of equations are included in those. So a graph volatility model consists of a two-dimensional system where X is the log price and is explicit from Y, as you can see. B and W are two correlated Brownian motion, and Y represents the volatility and satisfies a stochastic Volterra equation in one or several dimensions. In this case, it's just one dimension, but one can think of several dimensions. And we say that it's rough because H is smaller than 1/2, and in fact, it's been observed that it should be around 0.1, so very, very small. And after some rescaling that I won't go into the details of, but after some rescaling, adding epsilons here and there, you'll have to believe me that this system falls perfectly into our framework of stochastic Volterra equations. Right, and now the examples that we want to fit in this. So those three examples are, I think, the most relevant from the literature. The first one is called the Raff-Steinstein model. It's the well-behaved one, it's the nice one, because Y is just a fractional OU process. The coefficients are Lipschitz, everything's well-behaved. So this fits perfectly into our framework without too much complication. The second one is the Raff-Bergomi model. It's quite popular, quite famous. Was one of the first to be proposed, and so here Y is explicit, so there won't be any problem with Y. But the problem is that sigma of Y is the exponential function, and as I said, we wanted to be able to allow for exponential growth and not only linear growth, and that's what it plays with. So Raff-Bergomi model is included in our framework too, because we were able to relax that assumption. And last but not least, the Raff-Heston model, where Y is a typical stochastic Volterra equation. The drift is Lipschitz continuous, but the diffusion coefficient is the square root process. So there are two remarks I have to make about this. The first one is that pathwise uniqueness for this solution, for this equation, is still an open problem. We don't know whether it holds, we don't know whether it doesn't. But if one assumes pathwise uniqueness, then the limiting equation that appears in the rate function it's not unique. In general, it is not unique. But using what we did, we were able to bypass that problem, which means that if pathwise uniqueness holds for this equation, then we still recover DLDP and DMDP that I presented, even though the limiting equation may not have a unique solution. Right, so just mentioned that there has been already work done on those models in the past. So everything we do, especially in large deviations, is not new. The moderate deviations is quite new. But yes, anyway, that's all for me, I think. So I'll just wrap it up by saying that we study stochastic Volterra equations, which are a conducive framework for rough volatility models, and we do so through the lens of large and moderate deviations, which can be proved in a unified way thanks to the weak convergence approach. And that's it. Thank you for your attention.